My name is Shen, and I'm here presenting our work titled Sampling Quotient-Ring Sum of Squares Programs for Scalable Verification of Nonlinear Systems. Sum of Squares programs are very popular for Lyapunov-based stability, robustness, safety verification, and by extension, controller synthesis for a wide variety of dynamics, and not only algorithmically, but also demonstrated on hardware as well. The key idea behind SOS-based verification is that Lyapunov theories involve checking function signs. And if we focus on polynomials, a sufficient condition for non-negativity is that it can be written as a sum of squares of polynomials, or equivalently, this capital F of x admits a factorization written as M transpose QM, where M is the so-called monomial basis, and the gram matrix Q is PSD. So searching and checking for this Q matrix is an SDP, obviously, but the size of the SDP grows with respect to the number of indeterminates as well as the degree of the polynomial. In standard approach, the growth is binomial, so pretty rapid. This is one of the reasons SOS-based verification methods are currently only scaling to about 12 to 15 states, which is rather modest. We say one of the reasons because we're going to identify some other major culprits. But before we get to that, let's first formally set up the problem. So we assume the system dynamics and a fixed positive definite polynomial Lyapunov candidate V are given. We consider the task of approximating the system region of attraction, RA, using the sublevel set of V. And we consider three types of dynamics: polynomial subject to additive Lorentz type uncertainty, and rational trigonometric, which is commonly found in mechanical systems. So pretty standard setup. The only major motivation here is to improve the scalability. Towards that, I think it's helpful to examine why scalability is a challenge in the first place. Here's the standard SOS-based verification pipeline. We usually start with a Lyapunov or a system constraint sign condition. We massage that into a SOS condition, and through monomial basis embedding, we get an SDP at the end. We've sort of touched on how the final two stages are computationally expensive earlier. And indeed, most existing scale improving work, rightly so, addresses these two issues, although since they usually rely on special system structure or optimization relaxation, they are either non-general or conservative, so there's a gap there. But the bigger gap seems to be that so far, the overheads or inefficiencies coming from the first two stages are rarely addressed or even acknowledged. We will discuss the details in a little bit, but for now, let me just hit the note and say the standard approach relies on inequality-based set implications and auxiliary multipliers and or indeterminates for the sake of having convex formulations. And those are mathematical overheads, and they lead to bloated SDPs at the lower end. So what we propose here is, well, first, new general formulations to address the mathematical overheads, and then a direct application of a recent sampling variety approach to improve the lower level optimization computations as well. The end result is a much improved scalability to 32 states multi-reachability robotic system, or when a baseline is available, a 2 to 3 orders of magnitude speed up. And all the while, we have theoretical guarantee that the region of attraction approximation that we get is less conservative. So let's start with the polynomial dynamics case. Recall that condition 1 is our goal. The traditional approach relies on a straightforward interpretation of this condition, demonstrated in the animation here. We have two surfaces. The pink one is V, green one is V dot, which implicitly encodes the dynamics. Traditional implications as well. As I increase the level on V, I will get bigger and bigger sublevel set. I'll simply check to see if the states in those sublevel sets satisfy the V dot sign condition. And as we alluded to in the previous slide, to formulate this straightforward interpretation into a convex optimization, one needs to use the S procedure and a sign constraint Lagrange multiplier. And we call this formulation IE, inequality constraint formulation. What we proved in the paper is a much simpler equality constraint formulation. I'm putting the formulation and formal statement up here, but the idea is pretty simple. And let me try proof by picture. Unlike the traditional interpretation, we first take a look at the V dot surface. Under the mild assumption that the Hessian of V dot at the origin is negative definite, the origin is a local max. Therefore, locally around the origin, we must have V dot strictly negative. Since the system is locally stable as I move further away from the origin along the green surface, I must eventually flip sign and get to some strictly positive v dot. Since v and f are both polynomial by assumption, so is v dot, and it is therefore continuous. Given that v is continuous and, given that v dot is continuous and that v dot changes sign eventually, zero crossings must occur at some states. And these zero crossings are precisely the yellow line that you see in this animation. If I can guarantee that, well, before I hit this yellow zero crossing, I am within the row sublevel set of V, then by contraposition, all the states within the row sublevel set must have negative V dot. And that's the idea behind formulation E, equality constraint formulation. Okay, so you might wonder, why bother with an equality constraint formulation? Well, in itself, we got rid of the expensive sign or SOS condition on the multiplier lambda, but more importantly, it's a stepping stone for a quotient ring SOS program. I think the terminology quotient ring SOS program is not very important for this slide. It's enough to know that it's based on exactly the same high-level idea we just proved for formulation E. I think it's more important to point out that there are 4 advantages of Q. The first 2 you can sort of see just by playing a spot the differences game on the 2 left-hand sides. In Q, there's no lambda times V dot, so the left-hand side is just plain simpler. The third and fourth have to do with the right-hand sides and are based on known algebraic geometry facts. So first, in Q, we have a new letter n, which just like m is a monomial basis, but it's a special one. It's the so-called Grosvenor basis, and it's known to be much smaller than the standard basis m of x. And finally, since Q encodes an algebraic variety, this curly v here, which by the way is a set of polynomial roots, whereas E relies on degree-bounded multiplier, Q is just known to be intrinsically stronger, or mapping back to our context, this formulation is going to give us tighter array approximation theoretically. So far, it's all good news. Q is strictly better than E in every possible way. And the bad news is getting the Grosvenor basis n of x is very difficult symbolically. This is where the sampling variety approach comes in. So this approach is entirely based on the work done by Diego and Pablo. The idea is that, well, let's just sample on the variety and require SOS condition to hold on those numerical samples. And the cool thing here is that, well, given finite random samples, we could have implications in both directions and guarantee the correctness of the sampled version. Continuing using the plot earlier to get the high-level idea more tangible, we now only have to check conditions on these blue dots instead of finding ways to encode the entire yellow line. So this is a significant reduction. I think it's worth a quick word on how is this reduction possible. The idea is closely related to general polynomial interpolation. Whereas we could match polynomials by coefficients, we could alternatively match them by evaluations at sample points. Of course, even in this trivial example, you see that the number and quality of the samples are very important. And that's the main question formally addressed in Diego and Pablo's paper. But as a mere user, let me just highlight that the entire algorithm involves simple operations like SVD or rank checking and results in a rank 1 SDP. So to recap, we have presented 4 formulations so far for the polynomial case. Each progression gives us some kind of edge, and the final sampling quotient ring formulation is the strongest, yet results in the smallest and structured SDP. Shown here are a few benchmark systems comparison. We achieve either better array approximation or significant speed up. This concludes the polynomial case algorithm and results. Now we move on to the second class of systems where the dynamics is a nominal polynomial f0 of x plus a Luray type uncertainty delta of x, which satisfies this inequality constraint. Or more visually, this uncertainty delta is sandwiched in between 2 boundaries, alpha of x and beta of x, both of which assume to be polynomials. So standard approach for analyzing such systems relies on an IQC type argument and introduces auxiliary indeterminates to encode the uncertainty. This is in addition to the auxiliary multipliers used to encode the sublevel sets that we saw earlier in the polynomial case. So to isolate those 2 issues, we highlight our formulation in global analysis. So the key observation that we had in this case is that for any fixed state x, The admissible uncertainty delta of x is simply a convex combination of the two boundaries, alpha of x and beta of x. This allows us to eliminate the auxiliary indeterminates and reduce the analysis to the two uncertainty boundaries. Effectively, we're analyzing two polynomial systems. And as we can see from this implication chain, our smaller formulation is in fact stronger than the standard approach. So finally, we consider mechanical systems where the dynamics are often rational trigonometrics due to rotational joints and potential energy coming from the equation of motion. Here's the dynamics of the classical card force system, which is made of one pendulum attached to the card. We need to invert the trigonometric mass matrix to get the dynamics here. The complexity here is that, well, as we increase the number of pendulums or links on the card, even at 3 links, the mass matrix already gets pretty messy. To invert this mass matrix symbolically at scale is obviously very challenging. In other words, even writing out the explicit dynamics can be difficult, let alone analyzing it. So our idea is that, well, since the inversion is the bottleneck, let's just not do the inversion. In other words, instead of dealing with explicit dynamics in an ODE, let's consider the implicit dynamics encoded by a DAE, differential algebraic equations. So this key change, combined with some pretty standard tricks, gives us an exact description of the dynamics. I'm going to skip all the algebras. The punchline here is that the description is now all polynomial equation forms, so we could again carry on the analysis just as in the pure polynomial case. Because of the additional complexities we took care of in the dynamics, the computational savings here are much more significant. In particular, the size reduction plots are all at log scale. So let me quickly skip the conclusion. Basically, we combine new formulations and sampling variety approach to achieve better scalability. But I think the true takeaway is that whereas we exploited some inherent system structures to discover hidden equality constraints and made use of the sampling variety approach, the high-level idea is much more generalizable than the specifics. Thanks.